Glutamic acid is one of the amino acids that's found in the human body that is able to make a protein. Now, just like all of the other amino acids, this is going to be in the L orientation. So this is L-glutamic acid. This is the one that's actually going to show up in a protein. But there is also a D amino acid version of this, where it's D-glutamic acid, switching the nitrogen and the hydrogen. By doing such, the whole molecule switches itself around. This D and L orientation have nothing to do with the absolute configuration of the alpha carbon. It only has to do with what this looks like in relationship to glyceraldehyde. So this is the D version. It looks like the D version of glyceraldehyde. So this is called D-glutamic acid. Let's just talk about the L version because we're talking about proteins. L-glutamic acid. Just like any other amino acid, there's going to be a pH at which all of these hydrogens are going to be attached. And then there's going to be a pH at which some of these hydrogens, specifically the ones that are at polar bonds, are going to start to detach. The carboxylic acid groups are the number one place where hydrogen is going to leave, acid being like the number one thing that makes hydrogen leave or accepts electrons to make hydrogen move in the first place. And if we're talking about the order in which these carboxylic acids are going to lose, the first one that's going to be lost is the carbon that's attached directly to this central or this alpha carbon, the chiral one that's able to have 4 different constituents or attachments. The hydrogen that's on the carboxylic acid there, first one to detach. And it does that at a pH of about 2.1. So way, way, way below where your body's pH is, which is about 7.4. This hydrogen is going to be lost from this. And so now this is going to be negatively charged. At the same time, this nitrogen, it's only supposed to have 2 hydrogens attached to it to be neutral. Because it's got 3, this nitrogen's carrying a +1 charge. So we've got a -1 charge here and a +1 charge here on this nitrogen. And so overall, those balance out to 0, +1 and -1 go to 0, but the overall molecule is not a 0 charge. There are spots that actually have charge. So if you see a molecule where there are 2, a negative charge and a positive charge on the same thing, but it overall equals neutral, this is called a zwitterion. So this is this zwitterion form at a pH of like 2 something. Now, we talked about 1 carboxylic acid, but this molecule has 2 carboxylic acids. There's a lot more places where these electrons can be shared in a lot of these other bonds. And so it's going to be a lot less likely, especially than the aspartic acid, to get rid of its hydrogen at a really, really low pH. It's still going to get rid of it pretty quickly, but not as low as what aspartic acid was. This oxygen is going to lose its hydrogen at a pH of about 4.3. So again, we're still way below what the body's pH is of 7.4, but it's above the one that was made this oxygen lose. 4.3, keep going up, keep going up, keep going up, finally get to 7.4. So at 7.4, this is what this molecule is going to look like, where there's no hydrogen here, there's no hydrogen here, but there's an extra hydrogen on this nitrogen. And this extra hydrogen that's left on this nitrogen makes it +1. We got a -1 and a -1. -1 plus -1 is -2, plus +1 is -1. So in the human body, this is the form of glutamic acid that is going to be the most common, the most prevalent. This carboxylic acid just lost a hydrogen, but if we're talking about how we name this amino acid, it's solely based on this R group. So now let's talk a little bit about this R group. We see on this R group, we've got 3 carbons. These carbons are all going to have some type of hydrogens attached to it, but then one of these carbons also has these 2 oxygens attached to it. When this hydrogen is attached to this oxygen on this is considered a carboxylic acid. But when this hydrogen is removed and it's just C and 2 O's, this is called a carboxylate. So if this hydrogen is removed from this oxygen on the overall molecule, we're going to end up having glutamate instead of glutamic acid. And so the one that predominates, or the one that's the most common within the human body, is glutamate, not glutamic acid. This nitrogen isn't about to lose one of these hydrogens until the pH is like 9.5 or higher. And so at the physiologic pH, or the pH your body's at, this hydrogen is going to stay attached to this nitrogen. So let's keep talking about this R group. If we look overall at all these bonds, there's more carbons here. There's more places where these electrons can be shared equally and balanced. And so this is going to have more of a non-polar region. These oxygens with this carbon is still going to be a very polar situation. More of the molecule is going to be non-polar than polar. And so this overall is less acidic than aspartic acid because it's got this extra carbon attached to it. Now, in addition to these molecules having polar bonds, we already talked about this hydrogen's gone. And so this is carrying an actual charge of -1. So it's going to be able to bind with something that has an actual formal charge of +1. And that is considered an ionic bond. And the ionic bond is much more strong than any type of polar bond or other types of bonds. So that's the one that matters the most. So if we're grouping this, yes, it's polar, but more importantly, this is an acidic amino acid. Glutamic acid, or glutamate, is not an essential amino acid. You don't need to eat it in order for it to show up in your proteins. Your body is able to make glutamate, or glutamic acid. One of the major ways it's able to do that is via something called transamination. And there's a lot of different molecules that it's either transaminating or making because of transamination happening in the first place. Glutamate has also a lot to do with how much nitrogen ends up in your urea, or the urine that your body pumps out. So there is some balance of that transamination. It doesn't just go to other molecules. Sometimes it gets pumped out as urea through your urine. Now, the other special thing about glutamate, at least the L form of glutamate, is that this is also a neurotransmitter, like all on its own. So this molecule in and of itself is able to go into the human body and send signals, get in the vesicles, get transported through an axon, get sent somewhere else. It's involved in neurotransmission of signals throughout the human body. In addition to being part of the building block of proteins, it also helps your brain function and regulate itself. Now, we previously mentioned how there was the D form of the amino acid as well as the L form of the amino acid. This is one of the rare amino acids where the D form is actually present somewhere. It's not present in human bodies, though. It's present in bacterial cell walls. So if you look at a peptidoglycan layer, you're going to have a peptide and then glycans, or some type of glucose or other sugar molecule. That polysaccharide chain of those glucose or other sugar molecules, all of those are going to be connected to one another via peptide linkages. And a peptide is just a small form of a protein, aka a whole bunch of amino acids bound together. And one of those amino acids, specifically on the bacterial cell wall, that is involved in this peptide linkage is D-glutamate, or D-glutamic acid. The L form of the amino acid is present to make a lot of proteins as well as help neurotransmission, but that D form is also helping create the cell wall of a bacterium. So if you're trying to target the bacterium and you know that, okay, I need to do something in the bacteria that the human body doesn't do, one of the molecules that you can target is the D-glutamic acid. You know how your tongue has like those taste buds to help you taste things? Basically what's happening when taste happens is that you've got different molecules that are going onto those taste buds, and that molecule binds to some kind of receptor. That receptor sends something else into your brain. Your brain's like, oh, that tasted sweet. Or your brain's like, oh, that tasted sour. So if that molecule that gets into your taste bud that sends a signal to your brain is glutamate, the signal that gets sent to your brain is that this tastes savory, or umami. So glutamate, that molecule is responsible for all of the savory tastes that you taste, or all of the umami. Anything that involves a really strong umami or savory flavor, that's coming because your brain registered that glutamate hit your taste buds.